Good morning, everybody. Hey, I got a neat little problem here that I consider to be a triumph of mathematical notation. This is called set builder notation here. And it's what it is. It actually reads, we're looking for a set of integers that have the property that this particular expression, this rational expression will also be a natural number. Okay, and a natural number, by natural number, I mean 1, 2, 3, 4, 5 ad infinitum. Now, you can kind of get a feel for what the problem's asking for by noting that x equals 4 is a member of this set. In other words, 4, just by inspection, 4 is a member of this set D, right? You know, it's supposed to be a 4 there. 4 is a member of this set because 4 minus 3 is 1, and we know the numerator evaluates to a natural number. So 4 is definitely in the set without even lifting a finger. But the question is, so this set is definitely not empty. So let's see if we can find any more elements. Now, towards that, we actually just use the division algorithm, or you can use synthetic division here. If you evaluate the numerator at 3, if you substitute 3 in everywhere you get an x, you'll get this remainder of 72. And you can use synthetic or long division to get the quotient. And in a way, you really don't need this quotient because this quotient is always going to be a positive integer anyway. So you could just as well replace this with q of x if you wanted to. We could call that the quotient of x, and we know it's going to evaluate to a positive, you know what I mean? So what you could really have just found would have been this remainder, and you note that since this is always an integer right here, this is always an integer, what we're looking for is tantamount to just determining when this guy right here is an integer. And that's going to happen precisely at the divisors of 72. That's going to happen exactly at the divisors of 72. So on the next page, we're just going to list all the divisors of 72 and set each of them equal to x minus 3. And that'll be the values, that'll be the set that comprises D. Okay, so let me clear this out and let's move along to the next page here. Now, y'all, again, on the very next page, we're going to list the divisors of 72, all right, and then we're going to make sure that x minus 3 is equal to each of those divisors, so this will evaluate to a natural number. It turns out there's 10 of them. And so, y'all, here are the divisors of 72. I think, no, actually there's 12, and you can actually figure out exactly what that is using the prime factorization of 72, which is, I think, 3 squared times 2 cubed. And so you would get 3 times 4 divisors. I think that's 12 right here. 1, 2, you can count them up, but I'm pretty sure there's 12 of them. Okay, but notice all I did was just set x minus 3. We set x minus 3 equal to each of these divisors. You know, for example, one of the examples would be to set x minus 3 equal to, let's say, 6. This is just an example. X minus 3 equals to 6. Again, just a single example. 3 is a divisor of 72. Okay, but notice that we see that 9 is in this set right here. There's 9 right there, okay? And so on and so forth. You go all the way out and you get this set. So we've actually constructed the set of divisors. And a nice, we're not going to check all these, but you could substitute any of these in, like say, for example, 39 cubed plus 39 squared plus 4 times 39 plus 24 divided by 36 is actually going to be a natural number. We've proved that conclusively here. Hope you guys enjoyed that. I kind of like that.